Okay, so today we'll solve GET 2021. This is a question from functional analysis. It's question number 35. Let L1 be the sequence space, means which are all such sequence which are summable. And the norm is given by this. Then consider the subspace of L1, all such sequence either n times xn and sum from n to 1, n equals to 1 to infinity is finite. Then we define a linear transformation from x to L1. T of x of n is given by n times xn. Then you have to check 4 options that T is closed or bounded or not bounded, T is bounded, neither closed nor bounded, T inverse exists and is an open map. So which one is correct? You have to check. Okay, so in order to solve this is the NPTEL reference. This you can check. Okay, let's start solving. So L1 is the such sequence space such that these are summable. And X is a subspace of L1 which is given that all such X in L1 such that n equals to 1 to infinity n times mod xn is finite. Then we are defining a linear operator from x to L1 which is given by T of x at the point n is given by n times xn. Okay, so this is the linear operator from x to L1. Note that why this is well defined. So we are taking a vector from x and we are sending it to n xn. For all such element, if it is in x, then n xn is finite, means n xn is in L1. So therefore this is its n xn is lies in that space L1. So therefore this is well defined. Okay. So now we have to check that T is closed or bounded or 1 1 1 2 or not, or open map or not. First we will show that T is not bounded. This is T is obviously linear. Yeah. So now note that T is not bounded. So this is easy to check. So why? So we take that function. Suppose take at the nth point sequence, take a sequence which is at nth point it's take 1. Then if you plug it in T, it will give n. So and the norm of this is n, right? So therefore that can't happen. Okay, so let me write. T is not bounded. Why? So take defined. So first take a natural number. Gn at the point we are defining a sequence which is 1 if n equals to capital N and 0 if n not equals to capital N. Right. So what will be the norm of this? Note that X is a subspace of L1. So there we are also giving the L1 norm. So Gn So Gn is, note that Gn is in L1 X. Because it is only non-zero at 1 point, so it does obviously satisfy this condition. And what is the norm of Gn? So this is only 1 point, it's take the value 1. So its norm is 1, because at n equals to n it will means L1 norm. So basically summation n equals to 1 to infinity, and this is only 1 at n equals to n, it will be non-zero. So this has norm 1. What will be T of Gn? So T of Gn is n times Gn, right? And okay, now what will be the norm of T of Gn? Norm T Gn. Okay, so this is n, right? Because if n not equals to n, capital N, then this will be 0. So this is at, and the point if n is equals to, so this is n. So norm of T Gn, L1 norm. So this is, so only at the point n it's 1, so this is same as and otherwise it's 0. So this sequence is basically if n equals to n and 0. So therefore n equals to n, it will take the value n. So this is norm as n. Okay, and so can T be bounded now? So note that, T is bounded means T of G should be less than, or T of X should be less than C times norm X for all X in that space X, right? If T is bounded. But this, note that, but there does not exist any C positive such that norm T F is less than C times norm F for all F in X. Why? Because if this will happen, then we put F equals to, because because if this happen, then so for F is all such F in S, Gn is in X, then T of Gn will also satisfy this, or you will get n is less than C times, and this norm is 1, so n is less than C, but this cannot hold, right? Because you can, n is in natural number. For all n, right? But which is a contradiction. Because we can choose this n to be a sequence, so this is for all natural number. So means if you take this capital N to be large, then it will be only non-zero at that point, so there it will take the value, it is n. So basically it will be this capital N, right? So at the point n equals to n, we can write also capital N. Which is a contradiction. So which implies means there cannot exist a positive C so that this will happen, so which implies T is not bounded. So T is not bounded. So this linear operator is not bounded. Now we have to check that this is closed or not. Okay, so let's check. So now we will show that T is closed. So what does the mean a operator to be closed? T is closed means what we have to show? So to show if Fn be a sequence from X, and so Fn be a sequence which suppose Fn converges to F in X and Tfn converges to G in L1 because T map from X to L1, then T of F equals to G, that we have to show. So this means that T is closed. So if Fn converges to F and Tfn converges to G, then Tf should be equals to G. So this we have to show. Okay. So first note that convergence in X will imply pointwise convergence. Convergence in X imply pointwise convergence. Why? As you can see that f of n, this is always less than norm f x norm, which is L1 norm. So this is always true because this is the summation of Fn, right, for all n. So if something converges in the x norm, then it will converge as pointwise. Okay, so convergence in X imply pointwise convergence. So now we can show that T of F equals to G. So then for all m in natural number, what is G of m? So G is L1 limit of T of Fn. So this is the limit of n tends to infinity t of fn. So this is convergence in L1, right? L1 limit. Now what is limit n tends to infinity t of fn? This is t of fn is, so t of fn is basically at the point m, right? So again this is convergence, L1 implies pointwise, so we are writing it, so we can write gm for each m, this will hold, right? L1 implies pointwise. Now this, what is this limit n tends to infinity? This we can write, this is definition m fn m, this is definition of t. Now m, because this limit is independent, m can take it out, limit n tends to infinity fn m. And again we have shown that fn converges to f in x, and this implies pointwise convergence. So m, so this will converges to f of m. So due to pointwise convergence. And what is m fn? This is again t of fm. And this is true for all m in n, so therefore t of f is g. So that we have to show, which implies t is closed. Okay. So you have shown that t is closed operator. Now next we have to check the other option, or t inverse exists. So for that we have to check this is 1 1 and 1 2. So what is t? Not t is from x to L1, t of xn is nxn. Note that by definition, what is it is onto, t is onto, right? Why? For any y in L1, define x to be 1 by n y. So this is for all n. Then x belongs to x, because if you multiply n it will cancel and y is in L1, right? And t of x will map to so it is n times, so it is y. So therefore t is onto. And t is, why t is 1 1? T is 1 1 means let t of x equals to t of y. So means t of xn equals to t of yn for all n in natural number, means n xn is n yn, or n we can consider out, so xn equals to yn for all n natural number, so which implies x equals to y. So t is 1 1. So therefore t inverse exists. And so, and t inverse, let S equals to T inverse, and it will be given by Sx at n, it will be given by 1 by n xn. Okay, so T inverse x and given. Now what we have to check next? T inverse exit and is an open map. Okay, so you have to check that T inverse is open or not, or S. So first, for that, let's check that S is bounded. So note S is a map from L1 to X. Sx at n is 1 by n xn. What will be Sx norm? X norm. So this is summation 1 by n xn. So this you can always write less than n equals to 1 to infinity mod xn, which is the L1 norm of x, right? So which implies S is bounded. So S is a bounded operator, and okay, so S is also 1 1 1 2 also, because T is 1 1 bijective also. S is 1 1 and 1 2. Now let S is open. So assume S is open. Then what happened? Let's see. So as S is a linear operator, this is bounded means this is continuous. So we have so this is continuous map which is bijective and which open. So there is a one result that bijective continuous map, its homeomorphism if and only if it's open. So let me write a result. A bijective continuous map is homeomorphism if and only if it is open map. Now here what we have? Here S is continuous as S is bounded and linear. And bijective, continuous bijective and open map, because we have assumed S is an open map. So by the above result, S is homeomorphism. Means, so S inverse is continuous, because homeomorphism means inverse map is continuous. Now what is S inverse? Therefore S inverse is T, which is linear map, so T is continuous, implies T is bounded. But we have shown that T is not a bounded operator. It's not bounded. So therefore our assumption is wrong. We have assumed that S is an open map, so this is not true. So S is not an open map. S or T inverse is not. Okay. Okay, so now let's see which option is correct. T is closed but not bounded, that we have shown, so A is correct. T is bounded, so this is not true, B is false. T is neither closed nor bounded, but T is closed, so this is also false. T inverse exists and is open map, but T inverse exists but this is not an open map, so D is also false. So only A is the correct option. Okay.